Hello and welcome. Today we are taking a gentle journey into infinite sets, exploring the fascinating mathematics of forever. Let us begin with part 1. Before we can step into the infinite, we must first ask, what exactly is a set? In mathematics, a set is simply a collection, or you can think of it as a box of things. The things we place inside this box are called elements. Let's look at a simple finite example. Let W be the set of days in the weekend. We write it out like this. W equals the set containing Saturday and Sunday. This set is finite. It has exactly 2 elements inside of it. Because it is finite, you can easily finish counting them. But what happens if the box never gets full? Stepping into the infinite requires a shift in how we see things. An infinite set is a collection where, no matter how long you count, there is always one more. Think of a simple number line. 1, 2, 3, 4, 5. In mathematics, those 3 little dots at the end carry a profound meaning. They simply mean keep going forever. Let's look at our first example, the counting numbers. The most famous infinite set is the natural numbers, which we call n. The set n contains 1, 2, 3, 4, 5, and keeps going. The rule is very simple. You start at 1, and you add 1 to get the next number. Because you can always add 1 more, you will never run out of numbers. It is truly infinite. But what if we decide to go backwards? What if we include 0 and all of the negative numbers? When we do this, we get the integers, which we call z. The set z contains numbers like -2, -1, 0, 1, 2, and so on. Notice the 3 dots on both ends. This set goes on forever in both directions. This naturally brings up a question. Is the set of integers bigger than the set of natural numbers? To answer this, let's learn how mathematicians actually measure forever. How do we measure infinity? The secret is matching. Imagine you have a room full of people and a room full of chairs. How do you know if there are exactly enough chairs for everyone without actually counting them? It is quite simple. You just tell everyone to sit down. If every person has a chair and no chairs are left empty, you know immediately that the sets are the exact same size. In math, this perfect pairing is called a 1-to-1 match, or a bijection. Every person matches with exactly 1 chair. Now, keeping that idea of matching in mind, let's look at a mind-bending fact. Let's compare all of the counting numbers, the set n, to only the even numbers, which we will call e. Imagine lining them up together. The number 1 matches with 2. The number 2 matches with 4. The number 3 matches with 6, and 4 matches with 8. Every single natural number matches perfectly with an even number. All you have to do is multiply by 2. The conclusion here is quite beautiful. Even though your intuition tells you there should be half as many even numbers, because they pair up perfectly forever, the 2 sets are exactly the same size. Welcome to part 2. Let us continue our journey and take a step further into the infinite. Before we go deeper, we need to understand what exactly is a grid point. Imagine a perfectly flat world covered in a giant, never-ending piece of graph paper. In this world, every intersection is an address made of exactly 2 numbers, written as x and y. The first number, x, tells you how many steps to walk left or right. The second number, y, tells you how many steps to walk up or down. For example, if we start at the center, 0, 0, and want to reach the address 2, 1, we simply walk to the right 2 steps and up 1 step. Now, we encounter the problem with an infinite grid. Because our integers go on forever in both directions, we can create a grid of these addresses that never, ever stops. This brings us to a fascinating puzzle. How do we match a single one-dimensional list of counting numbers, 1, 2, 3, and so on, to an entire two-dimensional grid? You might think of just counting across, but if you start counting straight across, one row horizontally, because the row goes on infinitely, you will keep counting forever. You will never, ever reach the next row above it. To solve this, mathematicians use a beautiful visual proof, the counting spiral. To guarantee that we hit every single point on this endless grid eventually, we must change our path. Instead of going in a straight line, we count in a spiral, starting right from the center. We count 1, then move to 2, circle around to 3, 4, 5, and keep spiraling outwards. Because the spiral always grows outwards and never gets trapped on an endless path in a single direction, every single two-dimensional point eventually gets exactly one counting number. Therefore, we arrive at an astonishing conclusion. The set of natural counting numbers and the entire two-dimensional plane of integers are exactly the same size. This brings us to our first mind-blowing deduction: fractions. Think about what a fraction, or rational number, actually is. It is simply a number formatted as a numerator over a denominator. Do you notice anything familiar? A fraction is defined by exactly two integers. For example, the fraction 3/4 is essentially just the grid point 3, 4. Because we just proved that we can map out the entire two-dimensional grid using our counting spiral, we can also use it to map out every possible fraction. By simply skipping over invalid points where the denominator is 0 and skipping unsimplified duplicates like 2/4, our spiral will eventually hit every unique fraction. The conclusion here is staggering. There are exactly as many fractions in the universe as there are plain, whole counting numbers. But our journey doesn't stop at 2 dimensions. Let's look at our second mind-blowing deduction: 3D, 4D, and beyond. We just proved that a one-dimensional line of counting numbers is the exact same size as a two-dimensional grid. So what about a massive three-dimensional universe of points? If we take a 3D coordinate, x, y, and z, we can simply group the first two numbers together. We already know from our spiral that any two-dimensional coordinate, x and y, can compress down to a single counting number, which we will call n. Now our 3D coordinate has become just two numbers again, n and z. This is just another two-dimensional grid, so we simply compress it again. This reveals a profound multi-dimensional truth. An infinitely expansive three-dimensional space, a four-dimensional space, or even a 100-dimensional grid of integers has the exact same amount of points as a simple one-dimensional line. Welcome to Part 3. As we enter the final chapter of our story, we arrive at the most profound question yet. Up to this point, you might be wondering, wait, are all infinities exactly the same size? To answer this, we must meet the real numbers. These are all the numbers that make up a perfectly continuous, unbroken line. This includes every single never-ending, non-repeating, irrational decimal you can possibly imagine. Numbers like 0.1, pi, which starts as 3.14159 and goes on forever, negative 8.22, or the square root of 2. We just saw how brilliantly the fractions match up perfectly with our simple counting numbers. But can we do the same here? Can we match the incredibly dense, continuous line of real numbers to the simple counting numbers too? The answer reveals a much bigger infinity. A brilliant mathematician named Cantor proved that you actually cannot match decimal numbers to counting numbers. To understand why, let's imagine we tried to make an infinite numbered list of all the decimals anyway. Number 1 pairs with a random decimal, say starting with 0.3. Number 2 pairs with another decimal, number 3, number 4, and so on, continuing downward forever. Cantor stepped back and looked at this infinite list. He realized a profound truth and said, I can build a brand new number that is mathematically guaranteed to be missing from your list. Here is his beautiful method, known as Cantor's diagonal trick. He said to look closely at the diagonal digits of our list, the first digit of the first number, the second digit of the second number, the third digit of the third number, creating a diagonal line downwards. Now follow one simple rule. Just add 1 to each of those diagonal digits. The 3 becomes a 4, the 8 becomes a 9, the 7 becomes an 8, the 0 becomes a 1. By doing this, we have constructed a completely new number, 0.4981, continuing forever. But wait, you might ask, could our newly created number just be hiding somewhere, much further down on our infinite list? Could it be the billionth number? The answer is a definitive no. Let's check the list, digit by digit. It cannot be the very first number on the list because we specifically changed the first digit. 4 is different from 3. It cannot be the second number on the list because the second digit is different. 9 is different from 8. It cannot be the third number because the third digit is an 8 instead of a 7. And if you scroll all the way down to the millionth number on that endless list, it cannot be that number either because we deliberately changed the millionth digit. This brings us to our ultimate conclusion. Because this newly constructed number disagrees with every single number on your infinite list by at least one unique digit, it is forever missing. No matter how you try to count them, there are always decimals left over. Therefore, the infinity of real numbers is strictly, measurably larger than the infinity of natural numbers. Some infinities really are bigger than others. Let us take a moment to look back and summarize our journey. We learned that an infinity is a collection that never ever ends. We discovered that mathematicians measure the sizes of infinity by matching things up, using perfect one-to-one pairs called bijections. We found that the counting numbers, the integers stretching in both directions, and the endless sea of fractions are surprisingly all the exact same size. We saw how an infinitely expanding two-dimensional plane, or even a three-dimensional space, can be beautifully unwound and counted with a single simple line. But finally, we discovered that the smooth, unbroken continuum of the real numbers breaks this pattern entirely. It represents a truly, fundamentally larger infinity. Thank you so much for joining me on this journey, and thank you for exploring infinity.